right, so we're going to start our second day of quadratic functions notes by deriving the quadratic formula. And again, we can use complete the square to derive the quadratic formula. If you remember from yesterday, we derived the formula for how to find a vertex using complete the square. And I said here, hopefully I said this in class too, you might start to see some like familiar pieces or some echoes of the quadratic formula. And that's because we would get to this point using complete the square to work on our quadratic formula. So before we get to the formula itself, reminder, the quadratic formula is used to solve any quadratic f of x equal to 0. So when is f of x equal to 0 for the x values, whatever and whatever? Quadratic formula solves that for you. It solves it whether a quadratic function is factorable or not factorable, whether it has 3 terms or not. You can sub in an a, b, and a c. So you might already know the quadratic formula. Hopefully you do actually and have used it quite a bit. But again, I think it's nice to show you where things come from and kind of prove some of this stuff too. So I'm going to take this from, actually one more note here. So use to solve when any quadratic f of x is equal to 0. In other words, you're finding zeros of f of x, or x-intercepts, or whatever. We've talked about how that's all the same thing back in chapter 1. So from the vertex formula box, we got to this step. F of x equals a times x plus b over 2a squared. And then we had this plus c minus b squared over 4a. This is where we got our vertex formula from. So if I were really starting from scratch, I would have said, start here, start completing the square. Okay, now we want to say, instead of f of x equals, we want to say, when is this equation equal to 0? We need to solve this thing for x. If I want to solve for x, I would like to start by moving the c and the b squared over 4a to the other side of the equation. So let's make it b squared over 4a, because I would add that. Then I would subtract c, and that would be equal to a times x plus b over 2a squared. And now here's where I do want to go ahead and get a common denominator here. C needs to get multiplied by 4a over 4a. So this is going to become b squared minus c times 4a is 4ac all over 4a. Again, you might be seeing some like pieces of your quadratic formula that you've already memorized coming out. What's the next step to isolating x? Divide by a. If you divide by a, it's like saying times 1 over a. So I want to bring this up here. So now we have b squared minus 4ac, 1 over a times b squared minus 4ac over 4a puts a 4a squared in our denominator. And now it's equal to x plus b over 2a, the quantity squared. Next, we need to get rid of the squared by taking the square root. When you square root a fraction, it's best to square root the top and the bottom separately and remember your plus or minus. So I can't simplify plus or minus the square root of b squared minus 4ac, even though there is a perfect square in the b squared and a perfect square on the 4, the minus ac part messes everything up. I can square root the square root of 4a squared, that's 2a. Now, technically, should it be the absolute value of 2a? Sure, but honestly, there's a plus or minus here, so it doesn't really matter. Like, if that's positive, whatever, we're going to plus or minus in the end anyway, so you're going to get a plus and a minus version. If 2a is negative, same thing, you're going to get a plus or minus. And that is now equal to x plus b over 2a. Our last step is to subtract b over 2a. And I want to write this. Well, no, I'll just write it like this. Negative b over 2a plus or minus square root of b squared minus 4ac all over 2a. And just to clean it up into the quadratic formula that we all know and have learned already, these are both over the same type of denominator. So our quadratic formula, to get straight from general form to solving for the zeros, x equals negative b, or opposite of b, plus or minus the square root of b squared minus 4 times a times c. All of that is over 2a. This is the quadratic formula. You definitely need to memorize it. I know everybody has like the quadratic formula program or whatever in their calculator, but the amount of mistakes I get every year when you're not allowed to use a calculator just because you haven't practiced doing this math is unreal. So please make sure you have it memorized and that you know how to simplify these steps, which is what we're about to practice. Okay, do we have to derive the thing every time? Absolutely not. That's why we have this formula. So remember, you're going from a general form, y equals ax squared plus bx plus c. So the a, b, and c that we refer to are the coefficients in front of these numbers. All right, with all of that said, find the x-intercepts of the quadratic function. So you need to show that you're setting f of x equal to 0. F of x equals 0. I would just make that statement when x equals negative 6 plus or minus square root of 6 squared is 36 minus 4 is built in times a times c all over 2 times a. It is the square root that messes everybody up. So here we go. I do it this way. Ignore the 36. What is negative 4 times negative 1? 4. What is 4 times negative 8? Negative 32. So we have negative 6 plus or minus. So really this is the square root of 36 minus 32. It is the addition and the subtraction, the plus or the minus sign, that messes people up. You've got 3 negatives here, should be a minus. Square root of 4 is really just 2. Now I'm getting something that doesn't involve a square root. That tells me, hey, you probably could have factored this thing. So negative 6 plus 2 is 4 over negative, no, it's not. It's negative 4. Gosh, negative 4 over negative 2, which is 2. Negative 6 minus 2 is negative 8 over negative 2, which is 4. So could I have factored this into x minus 2 and x minus 4? Let's see. I'm setting equal to 0. I'm going to factor out a negative because I don't like having the x squared term be negative. Yep, could have factored, right? Would have been way faster. And I could have avoided any mistakes of quadratic formula that I might have made if I were miscalculating. So find the x-intercepts of the quadratic function. Quadratic formula works every time, but it's not always the fastest thing. So don't just default to that. Make sure that you are using the most efficient way that you can. Same thing for g of x. I could say a is 1, b is 0 because there's no x term, c is negative 24. Or I could just say I'm setting x squared minus 24 equal to 0. That's not a difference of squares, but I can isolate x squared. I can square root both sides. Square root of 24 is 2 radical 6. And that gets me to my answer. Okay, what about h of x? So I can consider factoring this. I don't think I'm going to get any combinations of 4. That's going to be 8 and 1 to give me 3 in the middle. I don't think so. There's no GCF, so this can't be a 4 and a 1. And for the same reason, it can't be a 2 and a 2. So factoring doesn't work. I do need quadratic formula for this one. So h of x equals 0 when x equals, opposite of b is positive 3, plus or minus, square root of 9 minus 4 times 2 times negative 4 all over 2a, 2 times 2. What's underneath the square roots? Negative 4 times 2 is negative 8. Negative 8 times negative 4 is 9 plus 32. So that's the square root of 41. So 3 plus or minus the square root of 41, which doesn't simplify, all over 4. Leave it like that. All right, so quadratic formula works every time. It's not always the most efficient manner. So I always think consider factoring, or if it's not a trinomial or not a difference of squares, use the square root method. So we did linear regression early in chapter 1, and we're going to use the same steps, but quadratic regression. So if you need a refresher beyond what we're doing in class for like written out steps for how to do regression, go see the linear models. But otherwise, we're going to dive in and look at these quadratic models. So a study was done to compare the speed x in miles per hour with the mileage y in miles per gallon of an automobile. The results are shown below. So here's speed, here's mileage. Use a graphing utility to create a scatter plot of the data. So fire up your graphing calculator. Clear out any old equations that are in the y equals. Go to Stat, Edit, clear out any old stuff that's in there. Go to the heading, press clear, press enter. Clear, enter, clear, enter. Enter the speed in L1. Looks like they're going up by 5s until you get to 75. Just checking this. I have 13 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good. And then type in the mileage into L2. Right? Remember to go to second y equals and turn on the stat plot. Also set it up so that the x list is L1 and the y list is L2. So I need to do second 2 to make that happen. And then zoom 9 for stat. This definitely does not look linear. It's got a couple of weird points out of whack, but this generally looks like a parabola will be a curve of best fit. Okay, so we can try a quadratic regression. So use the regression feature to find a model that best fits the data. Write the equation, comment on its strength based on the correlation coefficient. That means you need to have R pop up on your screen. So if your calculator has been reset, remember to go to mode. Check stat diagnostics, it needs to be on. Okay. So let's do a quadratic model. We're going to go to stat, calc, option 8. No, not option 8. What am I saying? I'm so used to doing that. Sorry. Quadratic regression. There's only one choice. Option 5, L1 and L2. I still want this to put the curve into Y1 for me. So alpha trace Y1. Calculate. This does not give me R, but it does give me R squared. So I'm going to write that down. And I'm also going to write down my equation. So let's see. So we have, instead of, oh no, it was y and x. So y equals negative 0 point, use all of the decimal places. You don't want to round to 3 right here, because if we do that on our AP test and we're off by a little bit, we might lose the point for that part of the problem. So I'm writing all of this down. And I'm writing down the r squared. Now correlation is r. R squared is literally just squaring your correlation values. So if you take stats, you'll get more into what it means. But mathematically, to figure out what the correlation is, we can say what's the square root of 0.978145185. So r is 0.9. Now this I'm going to round because I'm not going to do anything else with it. 0.989, that's awfully close to 1, so that indicates a pretty strong model. And take a moment to press graph. So our curve of best fit is a pretty good fit. The points that are kind of straying are these weird ones right here. Okay, so this question said write the equation, comment on the strength. So I'm just going to write fairly strong model to fit the data. All right, approximate the speed at which the gas mileage is the greatest. So take a look at your graph. Approximate means don't pick the greatest one out of this list. So our answer is not going to be 45 at 30.4. We want what the model says. It should be something close to that. But we're going to do second trace. We want to find a maximum. And see how you can see that you're on the model here because it says y1 equals. So remember how this works. You go a bit to the left of where you think the max is, press enter, a little bit to the right, press enter, have it guess. So like I said, it should be close to 45, but we're going to round to 3 places here and say, it says approximate the speed. So the speed is about 45.462. 45.462, always label. The speed is labeled in miles per hour for max gas mileage. Find the average rate of change between the speeds of 15 miles per hour and 45 miles per hour. Remember what this is going to do. Average rate of change. This is super common for our AP pre-calc test. Like we will absolutely have this as part of our free response question. Given some sort of function, find an average rate of change. All this is doing is sketching a secant line between those 2 points and finding the slope between those 2 points. So remember, average rate of change is simply the slope between those 2 points. So that's going to be 20, start with the bigger one. So that's going to be, let's make this y of 45 minus y of 15 over 45 minus 15. I like to have a little formula to write out. I do that for, you'll be doing this for AP Calculus as well, so it's nice to have something to show your work for. And then that's going to be 30.4 minus 22.3. 45 minus 15 is just 30. And quit to your home screen. So 30.4 minus 22.3, divide that by 30, means 0.27. What is the label on this? I know it just said find it, not to interpret it, but you should get in the practice of labeling. So remember, this is change in y. You think of it as change in y per x. Okay, so this is the change in the gas mileage. So 0.27 miles per gallon. I would write the word per instead of another slash, but per mile per hour increase in x. So basically we're saying on this interval, it's your graph again, the gas mileage is increasing at an average rate of 0.27 miles per gallon with each 1 mile per hour increase in speed, we're saying. So for every mile per hour you go faster, you gain that 0.27 miles per gallon. Labels like that are weird, so that's why I just wanted to write that out. Use the model to estimate the speed or speeds at which the gas mileage is 26.5 miles per gallon. So this would be a calculator problem, right? Because we're using regression. You would need to show that you're setting your model equal to 26.5. Now here I might round or do something like this, just because I get kind of sick of writing the numbers. Or you could say like, one is what y is about equal to 26.5 when. That would probably be fine. I'm probably going overboard here. At x is about equal to. Okay, now remember, let your calculator do the heavy lifting for you. The screen is already zoomed in. In Y2, put our gas mileage that we want to see. There are 2 places, 2 speeds at which that happens. So find the intersection. Second trace intersect. Your calculator is going to find whatever intersection is closest. So just move your cursor a bit to the left and press enter. And then it says second curve, like yes, that's the other line. Enter, guess. So it'll hop to the one further left because that's where I was. So that's when x is about 23.565. 23.565. Always label miles per hour. And I need to find the other one. Second trace, intersect. I'm gonna get my cursor all the way over here. It's kind of slow on the computer. I don't have to get it all the way over, just further to the right. So enter, hop down to that line, enter, guess, enter. 67.358. Label that miles per hour. Okay, last regression example here. Table below shows revenues in billions of dollars of Netflix from 2010 to 2017. Now in class, I'm probably going to say, if you need practice, you can we might skip over this one if we're short on time. And if you need practice, come back and watch this video. We'll just have to see how the time goes. Use the graphing utility to create a scatter plot where 0 is 2010. So 0, 1, 2, 3, etc., all the way up to 7. All right, so go to y equals, clear out your old stuff so you don't get confused. Stat edit, clear those lists. Right. So 0 through 7. And type in the revenues. All right, now let's look at the scatter plot first. So the scatter plot should already be set up. You do zoom 9 to reset the window. Now, because of this point right here at 0, I'm not 100% convinced that this is quadratic. This says use the regression feature to find a model that best fits the data. So you can try quadratic. I would take note of the correlation and what it looks like against the scatter plot. So let's do this. Stat, calc. Let's start with quadratic. And go ahead and store the equation into y1. I'm not going to bother finding r, but r squared was I'm just going to say 9903. So this was for quadratic. Take a look at the graph. So it's a pretty good fit, but maybe we can get a little bit better. Let's look at some of the other choices. Stat, calc. What about cubic? Because it had that little dip to it. You can store this in Y2 if you want to compare all the models. That correlation is higher. If R squared is higher, then R is going to be higher, 0.9992. And let's look at it at that model. So there's quadratic. It's kind of hard to tell with the quadratic, but I think that does look like it follows the curvature a bit better. What about stat calc? We might as well try quartic. That would be like x to the fourth. And then we run out of options. It's not going to give us like to the fifth or whatever. So let's choose 7 just to see. Let's put this one in Y3. .9993, so not a huge difference. Let's check the, yeah, I think that black model's the best, right? It's very close to the red one, but let me turn off the other ones. I think we say quadratic's out, but let's just turn off the red one too. Slightly higher correlation, that's a really good fit for the fluctuations, slight fluctuation of those few years. So I'm gonna go with the quartic on this one. All right, so I need to calculate it again because it's gonna be off my screen. Just leave it alone, we don't need to store it again. And because I don't have a ton of space, I'm gonna round to, maybe I'll round to like 6 places. Usually that's what we can do in AP if we are not wanting to write out a million decimal places. So y equals negative 0.001686 x to the fourth plus 0.05636 x to the third minus 0.277102 x squared plus 1.109728 x plus 2.193106. This model has highest correlation and fits data in scatter plot the closest. Approximate Netflix Incorporated's Netflix's, I don't know, that sounds weird, revenues in 2018. So we've got to 2017. This is extrapolation. I don't know if it's accurate or not. How do we do that? We go to the graph and we say second trace value, 18. No, wait, not 18, 8. Because remember, 7 was 2017. Why does it say error invalid? Well, my window, quit that. My window, the way it's zoomed, doesn't actually go to 8. Okay, so what if the value you're finding is outside of your window? Then use your home screen. So remind yourself where your function is, y3. Use function notation on your home screen. Alpha trace y3 of 8. That's what I want to find. So that is 15 point, let's round it to 297. This is talking about money, revenue, 15 point, what was it? 297 billion dollars. That's a lot. I already have the dollars in there. Billion in 2018. What type of concavity does the model show? So if it were quadratic, it would have been concave up the entire time. So first let's tackle concavity. Go back to your graph. Looks to be concave down, and then maybe right here-ish. What is this? This is 1, 2, 3, so maybe 2013. Then we switch to concave up. So I'm going to say concave down from 2010 to about, because I don't know for sure, 2013, and then concave up from 2013 to 2017. Is the rate of change increasing? Is the rate of change, is the slope, are the slopes increasing at an increasing rate or decreasing rate? Now, I think that I had to change this because I assumed we were doing quadratic. So let's just say changing, because it's not always increasing. Is the rate of change changing at an increasing rate or a decreasing rate? So go back and look at the graph. Imagine that you're drawing in slopes. If a graph is concave down, the slopes should be decreasing. And let's just check that. So we've got these positive slopes and they're sort of zeroing out. When you switch concavity, you get like a slope close to zero and then it starts to get steeper again. So for the 2010 to 2013, the slopes or the average rate of change is decreasing. Concave down always means decreasing. And then from 2013 to 2017, average rate of change is increasing. Concave up always means increasing. Okay, here's an AP question. This is the last thing that we're doing today. This is, again, guaranteed question on your AP test. Something along these lines. The table shows values for a function g at selected values of x. Which of the following claim and explanation best fits these data? So take a quick look at the claims. This is a linear function. This is a linear function. This is quadratic, quadratic. Okay, so first let's figure out, is it linear or quadratic? A linear function, the common differences would be the same. So actually, I want to do this. Let's do steps. So linear versus quadratic. What do we do? Step one is make an average rate of change column. Often these tables go up by 1, so you're really just finding the difference between each consecutive set of numbers. But if this went like 0 to 1, then to 5, then to 13 or something, I would just find the slopes between each of those points. So find those slopes. And then make another column, make a differences in the average rate of change column. If the average rate of change is the same for every single column, so if I find the average rate of change and the slope is always 2 or whatever, then it's linear. But if I get different average rates of change, then I check to see, well, are they different by the same value? So let me show you what I'm talking about. Average rate of change, which are basically slopes. Now, you have nothing to fill in for this first line. But what's the slope between g of 1 and g of 0? So 78 minus 53 over 1 minus 0. What's 78 minus 53? 25. So the first slope there is 25. Now, if the next slope is 25, and the next slope is 25, and the next slope is 25, that means g is linear with a slope of 25. So let's see. The next slope between g of 2 to g of 1, 97 minus 78 over 2 minus 1. 97 minus 78 is 19. Not the same, right? Okay, that doesn't automatically, well, you know what? I guess in this multiple choice problem, that automatically puts us to quadratic. But I just want to show you what's going on here. So let's find the next slope. 110 minus 97 over 3 minus 2. 110 minus 97 is what? 13, right? Minus 10 minus 3. 117 minus 110 over 4 minus 3 is 7. So these are not the same slope. It's not linear. Bum, bum. What are the two options if it's quadratic? Because the rate of change over consecutive equal length input intervals is constant, the rate of change is constant, or because the change in average rates of change over consecutive equal length input intervals is constant. It's saying almost the same thing except the change or the average rate of change. So Average rate of change, or the rate of change being constant, would be the reason it would be linear. That's this. These are not constant numbers. But what's the difference in the average rate of change? Nothing to subtract there. 25 minus nothing, can't do anything there. What's 19 minus 25? Or what's 25 minus 19, however you want to subtract that? Negative 6. What's 13 minus 19? Negative 6. What's 7 minus 13? Negative 6. This change, this delta, is constant. If we were doing a difference quotient on a quadratic equation, we would get a linear result, right? If we take the derivative of a quadratic, we get a linear function. So that's what this is showing you. So it's option D, the change in the slopes over consecutive equal length input. This just means we're going up by 1. Delta x equals 1 every time. That's constant. If this table didn't go up by 1s, I would still just find the slopes, and so I would be finding the slope per x. So that would be okay. All right, we're going to stop there for today's notes and just practice a lot of applications for the next couple of days.